Welcome back to Beyond the Textbook, the series where we explore the beautiful mathematics left out of the school curriculum. In our last episode, we uncovered the hidden power of Ptolemy's theorem. Today, we are cracking the Butterfly Theorem. Draw a circle. Draw a straight line across, and find its exact center point, M. Draw two more lines slicing straight through that center point. We will call them AB and CD. Connect the edges to make our butterfly wings. They cross our first line at two new points, X and Y. The theorem says the distance from the center to X is exactly the same as the center to Y. Let's prove it. Watch what happens when we move these chords. No matter their angle, as long as they pass through M, the distances to X and Y visibly remain perfectly equal. First, let's look at the angles of our wings. Angle A and angle C open up to the exact same top curve. The rules of geometry dictate they must be identical. Tracing the other way, angle D and angle B both open to this bottom arc. So they are identical too. Here is the secret to solving this. We are going to zoom in on the left side. From point X, we draw a line straight down to the blue chord at a 90-degree angle. Let's explicitly label the exact spot it hits as X1. We do the same thing to the other blue chord. We drop a 90-degree line down, and we will call that spot X2. Now let's pan over to the right side and do the exact same thing from point Y. Drop a straight line to the top chord, label it Y1. Drop a straight line to the bottom chord, label it Y2. Let's zoom back out to see what we've built. Look at this green triangle XA X1 and this green triangle YC Y2. Because they share a 90-degree corner and that green angle, they are similar zoomed versions of each other. That means dividing their dashed heights gives the exact same ratio as dividing their long sides. The purple triangles follow the exact same rule. Height divided by height equals long side divided by long side. Finally, look at these two tiny yellow triangles touching at point M. Because they meet at a point, they have vertically opposite angles and 90-degree corners, making them similar too. And the other two tiny yellow triangles give us our fourth and final equation. Here is a great algebra trick. We can multiply the left sides of our yellow equations together, and it will equal the right sides multiplied. Because it's multiplication, we can just slide the bottom pieces around. Let's write that in a cleaner way, and then we will see why this is so important. Now, notice the first fractions perfectly match left-hand side of equations 1. Second fractions perfectly match left-hand side of equations 2. Now we can substitute their right-hand sides over here. Okay. We are almost done. Now, let's consider the intersecting chords theorem, which tells us that when two chords cross in a circle, their chopped pieces multiply to the exact same number. For point X, the parts of the yellow line, XA times XD, must equal the parts of the white line, PX times XQ. Since M is center, the distance from M to the edge is half of the chord. Let's call it L. So, the left piece PX is just L minus this tiny bit XM. And the right piece XQ is del plus XM. In algebra, multiplying a minus and a plus simplifies to L squared minus XM squared. Doing the exact same process for point Y gives us L squared minus YM squared. Let's plug these answers back into our main fraction. To solve this, we cross-multiply. When we expand the brackets, the messy term xm squared times ym squared shows up on both sides. We can just cancel it out. Divide both sides by L squared, then take the square root. And there is our proof. M is perfectly centered between X and Y. Subscribe for more deep dives, and I will see you in the next episode.